So let's move to another important topic in our course, and this is about linear regression. So what is linear regression supposed to mean? How is it important? Whenever we consider any data which is correlated, which is relevant, it would have a trend. And can we have a relationship between the variables? Can we have a correlation between the data? That would depend on how strongly it is correlated or not. So how would we evaluate it? So we start with an example. Let's say we have data about our previous course where a student had been studying 2 hours per day, and he scored about, let's say, 50 at the end of the course. Or maybe this is the study hours per week, and these are the marks. This we say X, and this is not any student. And there is another student who studied 4 hours per week, and he was scoring 55. There was another one who was working 6 hours a week, scored 65. Another one was studying 8 hours a week, was able to score 70. Another one was studying 10 hours a week, was able to net 80. And this is about a particular subject, and he was studying this many hours per week. And this is in addition to the course lectures. And another one who was studying 12 hours a week scored, let's say, 85. And another one was doing 14 hours a week, was able to score in perfect A. So we have 7 data points, and let's suppose we have number 8 scoring 92, and number 9 18 hours a week, and was able to score 94, and number 10 was studying 20 hours a week, he was able to score a perfect 100. So if we want to do the whole thing, we can solve for every one of them, but I would restrict the data to 5 only for now, and then if you want, you can extrapolate it for the complete set as well, as per your leisure. So I'm not using this data for brevity of our calculations in this video, and instead I will be using the data only for the first 5 values. So if I consider the first 5 values, what do we get is we have these are the x values, because this is the independent variable. Everything over here depends on this one. Just adding them together, 2 plus 4, 6 plus 6, 12 plus 8, and then we get for 5 values, n is equal to 5. The sum of x is for us 30, and if we divide it by n, it is called mean of x, and mean of x for us is 30 by 5, that is 6. On the same time, if we add the marks that the student obtained, that turns out to be sigma y by n. We represent that as y bar, the mean value, and that is 64. So if we plot the data, if we plot the same data, and if we consider that student was studying 2 hours, 4 hours, 6 hours, 8 hours, 10 hours, and so on and so forth, and he was scoring where 50, 60, 70, because the largest value is 80, so I would include that as well. So for 2 hours case, we would have data over here. For 4 hours case, the data would be, data point would be something here, and for 6 hours, it would be something in here. For the next one, it is 70. For the next one, the 10, it is up there at 80. So apparently there is a straight line, but it is not absolutely straight line. It would turn around a bit. The data will be slightly up, slightly down. But the way we see it, the average is 664 somewhere over 246. It would be somewhere in here. This is our x bar, y bar. So once we get hold of the mean value, we can calculate the x, which is very important value, which is x minus x bar, y minus y bar. So if we take difference of 2 from 6 or 6 from 2, it would be the same thing, but I'm writing x minus x bar. For absolute terms, it would be the same thing, but for x minus x bar, it would be 2 minus 6. That turns out to be minus 4, minus 2, 0, 2, and 4. For this one, the difference would be 64 minus 50 minus 64 is minus 14. This would be minus 9. This would be 1. This would be 6. And this would be 16. Interestingly, if we had added them together, all these values, the sum would be 0. And if in case you do not get that 0, that means you have made a mistake adding or dividing them. Similarly, the sum of all these values would also be 0. That is very interesting, because although it would feel like how erroneous this is, how incorrect it is, this gives us an insight if we have the error in estimation, but errors don't go away. But apparently, this sum means that the error has just swept away somewhere. But if we take squares of all these, if it is x minus x bar squared, this is 16, this is 4, this is of course 0, 4, and again 16. Now if we add them and sum them together, this does not come down to 0. So the errors from the mean position is now a bit exploded, bit more than usual, and then we can safely assert that the correlation can be found out because of it. Similarly, for these, we had 196, for this 81 and 1, and for 6 it is, for this one it is 36, and for 16 it is 256. So now we have x minus x bar whole square and y minus y bar whole square. We can of course sum them together, and if we sum this and if we sum this, this sigma x minus x bar whole square can be calculated, and what we get from that is very, very important. Similarly, y minus y bar square summed up can be calculated. And there's another important one, which is the product of x minus x bar and y minus y bar. In here, if we multiply them together, this is 14 fours of 56. Let's see. If in for retrospective, I'm doing it here because I'm not left with enough space over there. X minus x bar, y minus y bar. So for this one, we have 56. For the next one, this is 18 and 0 and 12 and 64. We can of course sum them together, and if we sum them and solve them, we would have a very useful value, useful parameter. This is called the correlation coefficient, written as R equal to the product of differences quotient with product of squares of differences, sum of squares of differences, and sum of squares of differences. If I write y minus y bar or y bar minus y and then square it, it is absolutely the same thing. It turns out that for my case, for this particular case, the correlation coefficient turns out to be 150 by square root of 240 and 570, 570 for this and 40 for this, square root, and it is 0.99. So if R is equal to 1, that means a very good correlation. And the second thing which it shows is that it is, if it is positive, the slope would be positive. And had this term been negative because of one of these turning out to be negative, then the correlation would be correlation coefficient would be negative, and then we can in that particular case the correlation is negative. And if we don't get a very good number close to 1, then we say that the data is not so well correlated with each other. So what is the utility of the whole mess we've created, the very long calculation we have done? For a particular case, we had the equation for a straight line. See, this is a straight line and this is also a straight line, this is also a straight line. So what we can do is we can write y equal to mx plus c, and in that case m is slope and c is the intercept. So for this particular case, we are not writing m and c, instead we are writing a and b. So it would be x plus a, just to differentiate between this one and anything which we would be doing later on. So if I write this whole equation as slope of this one can be calculated using the same relation similar to this one, but this is b is equal to x minus x bar, y minus y bar, and the sum of the product of these two differences divided by sum of x minus x bar independent variable squared. So this constitutes the slope. And how would we calculate the intercept then? The intercept is very easy, to be honest, because we had calculated the mean x bar y bar already, and we know that if there's a mean, and it could be here or anywhere, if we have mean and if we have calculated the slope, then that would lead to somewhere where it would intercept the x-axis. Had the x-axis been here or here or here or whatever, we can calculate the intercept. So what I would do is I would make a trick out of it, because we write y equal to mx plus c, but in this case I would write slope, which is calculated from here, b, and I would use y bar minus bx bar as my excuse to find the intercept a with our x-axis. In this particular calculation which we are running right now, the intercept is 41.5 and the slope is 3.75. I've run the numbers beforehand for you, so it is done quickly. So the final regression equation, if we plug in the values of b and a, we get 43.75 x plus 41.5. So what is the utility of this equation? Is it any useful? Yes, it is very, very useful, because if you look here, we had the data from, let's say, 2 to 10, and if we had a student studying 2.5 hours or 5.5 hours or 6.5 hours or 7 hours, as long as it is between the data we have asserted or estimated or calculated, we can predict the marks for the student. It is very easy. In this particular case, if you plug in 5 over here and then calculate for the marks, we can do that. So this is very useful information. If I, for example, say if somebody studies 7 hours per week of the subject beyond the classroom, then plug it in, the marks would be 68. This is absolutely based on data. It is based on the information we had. So these particular set of calculations gives the spread and how far the x is varying or how far the y values are varying, and how the data is correlated, and how we can use this particular data, this equation which we inferred or calculated from the data, to calculate what are the marks possible for an unknown or unforeseen students' working capacity per week. Okay, this is what we had for linear regression. You can comment on a particular aspect which you did not understand. I can repeat that. Thank you. Allah Hafiz.